Hello again. So we are talking about conservation of mass using control volume analysis, and we just talked about applying conservation of mass to seeing how fast ketchup leaves a ketchup packet smashed by a bowling ball, where we made some rather ridiculous assumptions, primarily that the ball velocity remains a constant. There's a bonus video where we talk about what happens if the ball velocity does not stay a constant. You can look into that. And today we're going to talk about our semester-long design problem. And we're going to say the question we're trying to answer today is we're going to try to design our nozzle exit, and we're going to try to figure out what our largest nozzle exit area we can have. You don't quite know this yet. We'll learn this in a lecture or two, actually. But the force generated by each nozzle is equal to v squared rho times a, roughly speaking. So, or at least proportional to that. So if we can increase our area, we can increase our thrust. So we want to figure out what our largest area is because we'd like to have as much thrust as possible, right? Because we want to get this guy here, who is, in theory, me, as high as possible. So given a good pump, which has a delta P of 4 times 10 to the 8th pascals, which is quite high, and a Q dot max, a max flow rate of 4.1 times 10 to the negative third meters cubed per second. And these are the stats on a water jet cutter. So a pump used for water jet cutting. Again, a great YouTube dive if you have some free time. Great. So, what is the largest nozzle exit we can use? Well, let's step through this and figure it out. We want to relate velocities and areas to each other. What do we use, right? Or pressures and areas, right? But we know in our head that we can relate pressures to velocities. So we can go from pressure to velocity and velocity to area. So if we want to relate velocities and areas to each other, what do we use? We use conservation of mass. Conservation of mass. So the first thing we do always is draw a control volume. Always, 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 always draw a control volume. Just like with sum of all the forces is equal to mass times acceleration. If you don't do a free body diagram, then are you really doing some of the forces? No, you're not, right? You might make a mistake. We want to see you draw your control volume neatly and so that other people can understand it. So if we were to draw our control volume, remember we have a few rules about this that help make our analysis a little bit easier. I want you to try to remember them now. You can pause the video and try to remember them from 2-3 videos ago, depending on whether or not you watched the bonus video. So go ahead and think about them. All right, now you're back, and yeah, I don't know if you can hear my kid. So yeah, so one thing we want to do is we want to make sure that our fluid leaves perpendicular to our control volume. So we know that one of our faces is going to have to look like this, right? And then we're going to cut through some place where we know some stuff. Okay, so we're going to cut through right there. Because we know that after the pump, we're going to assume that the pressure here, P, is equal to 4 times 10 to the 8th pascals. At least. It might be a little bit higher, but at least that much. Cool. So we've drawn our control volume. We're going to simplify our problem now. So let's write out conservation of mass. We have 0 is equal to the d dt, the integral over our control volume of rho dv, plus integral over control surface of rho w dot n hat dA. So we're going to simplify our problem. Let's assume that density is equal to a constant. All right, we're going to call that A. A steady state. We can call that B. And we're also going to assume uniform flow out of our nozzle. So if we do that, steady state allows us to say that this is equal to 0. So that's B. Density is equal to a constant, so that we can take our density out here. But it's equal to 0, so we can just divide out that density. So, and that's due to A. And we can get rid of the integral due to C. So we're going to have, this is equation 1 to equation 2. We're going to end up with 0 is equal to the sum of rho times W dot n hat dA. Oh, not dA, sorry. We integrated, so it's just multiplied by A. Multiplied by A. Cool. And remember, it's because we have uniform flow at our entrance and exits that that allows us to convert from an integral to just a sum, where we're summing over all of the entrances and exits, but each individual entrance and exit is just rho times the velocity dotted into the unit normal of the surface times the area of the flow crossing that surface. Great. So, and that's C that allows us to do this. C. So 2 to 3, we're going to call this 1 and 2, 1 and exit, or 1 and exit, that'll work. Then we're going to say that 0 is equal to, so we have fluid entering our control volume. Oh, that's right, we can divide out the rho, by the way. We have fluid entering our control volume here at 1, and if we remember from our mnemonic, entering fluid is bad, so it's negative. So we have a negative omega, or W1, and it's times our area 1, A1, and that's going to be plus W exit times our area exit. We don't know this, and honestly, we don't know this or this, but we do know that area 1 is much, much larger than area exit. So, by the way, this should look very familiar. If we rearrange it, this is V1 A1 is equal to V2 A2. So we've been using this form of conservation of mass for quite a while now. And if you remember, this expression basically says that Q1 is equal to Q2, right? Because it's an expression of conservation of mass, and we were able to drop off the density because density is equal to a constant. So if V1 A1 is equal to Q1, W1 A1 is really just equal to Q max, right? This is equal to our maximum flow rate for our pump. So we know those combined. We don't know them individually, but we do know them combined. And now the question is can we get an expression for our exit velocity, WE? And for that, we're going to have to bring in our good old friend. By the way, step 3 here, we did the dot product right there. When we went from here to here, we did the dot product. And remember, because it was just a plus or minus 1 because we drew our control volume accurately. All right, so our good old friend Bernoulli's we're going to bring in. P1 over rho plus V1 squared over 2 plus G Z1 is equal to P exit. We're going to just do E over rho plus VE squared over 2 plus G ZE. Great. So we know that our velocities are not, our heights doesn't change hardly at all. So we're going to neglect our heights. We're going to choose gauge pressure. And remember, we need to draw a streamline for Bernoulli's in order to use it correctly because we have to know where our entrance and exit points are. So if we pick here and then draw out to here, where this is 1 and this is E, we can also assume gauge pressure. We're going to assume gauge pressure, which means PE is equal to 0. We'll call this D. So PE is equal to 0. P1 we know. V1 we don't know. And VE we don't know. But we do know that because V1 A1 is equal to V2 A2 from equation 2, or sorry, this is equation 4 here. Oh, we mislabeled these. That's my bad. I forgot to write. Oh, no, I didn't. 2 to 3. That's right. So from equation 3, we know that this is true. So equation 5 would tell us that V1 is V2 is equal to V1 A1 over A2, which tells us that if A1 is larger than A2, in fact, A1 is much, much larger than A2 because we have that here in our problem definition, then we know that V2 is much, much larger than V1. So if we go 4 plus 5 into 6, we have that our V exit, and we're going to do a little bit of simplification in our head now because this is basically equal to 0 because of 5. We know that V exit is equal to square root of 2 times P1 over rho. And that's just taking and solving for this V exit here. And all we have left is this over here. Great, which we can plug in. This is equal to 4 times 10 to the 8th pascals times 2 divided by 1,000 kilograms per meter cubed. And if we take the square root of this, we get that it's equal to 1,265 meters per second. I like that velocity. That's a great velocity. That's high, right? As we mentioned above, we'll learn in a lecture or two that our thrust is proportional to v squared rho times a. So if we can get that high of a velocity, hint, we can't actually, but if we can get that high of a velocity, then we can get a tremendous amount of thrust. Cool. So yeah, that's our velocity, our exit velocity. And we wanted to figure out what area would give us this exit velocity, right? Because we're constrained by our flow rate. Because we want to achieve our maximum flow rate. Because we want as much thrust as possible. We want as much material moving through this device as we can at its maximum pressure, right? Because if it moves through it lower than its maximum pressure, then our exit velocity decreases and our thrust decreases as well. So we're trying to keep our maximum pressure but also meet our maximum flow rate. And to do that, we then take 6 plus 3, and we know that V1A1 is equal to, we'll just say equal to Q max, which is equal to A2 times V, or A exit times V exit, but we know V exit. So we can plug everything in and we get that A exit is equal to, what did we say was our flow rate? 4.1 times 10 to the negative third. 4.1 times 10 to the negative third meters cubed per second, divided by our velocity, which is 1265 meters per second. And hopefully you're starting to see something here. We find out that our area is equal to 3.2 times 10 to the negative 6. 3.2 times 10 to the negative 6th meters squared. So this is roughly a 2 millimeter diameter jet. 2 millimeter diameter jet. That's quite small. Oh, and just as a reminder, in order to use Bernoulli's, we also had to assume inviscid flow. D. Cool. So, yeah, we found out with a good pump that we found, which was a delta P of 4 times 10 to the 8th pascals at a Q dot max of 4.1 times 10 to the negative third meter cubed per second gives us a 2 millimeter diameter jet, or a 2 millimeter diameter exit hole.